All right, let's jump right into one of the biggest geological mysteries out there. We all know our planet is alive, right? It's constantly reshaping itself from the inside out. But what if I told you that for the first chunk of its life, Earth was, well, quiet? That is the cold case we are cracking open today. When did our planet's great geological engine finally roar to life? Right now, the very ground beneath our feet is broken up into these massive tectonic plates that are always on the move. This is Earth's engine. It's the powerhouse behind the most dramatic stuff we see. The violent shake of an earthquake, a volcano blowing its top, and the slow, unbelievably powerful rise of mountain ranges like the Himalayas. It's absolutely fundamental to the Earth we know and live on. But here's the kicker. A whole lot of evidence suggests this engine wasn't always running. For maybe a billion years, maybe even longer, Earth might have had a solid, unbroken shell, just one single static lid covering the whole planet. Just try to imagine that. A world with no continental drift, no subduction, a geologically quiet and totally different place. And that gets us to the big question, right? If Earth wasn't born with plate tectonics, then when did it start? When did the planet's crust finally crack apart and start this incredible dance of creation and destruction that we see today? And believe me, this isn't just some fun trivia question. It's one of the most profound and fiercely debated mysteries in all of Earth science. So how do we even begin to solve this? Well, we could start by asking the experts. The only problem is, they don't agree. Not even a little bit. And I'm not talking about a small disagreement here, a few million years here or there. No, the proposed start dates for plate tectonics span almost the entire 4.5 billion year history of our planet. That is a truly massive range of uncertainty. So you've got these different teams of scientific detectives, and each one has their own clue. One camp looks at these tiny, super resilient zircon crystals from way back, more than 4.2 billion years ago. And they see chemical hints that tectonics was already happening. Then another group points to rocks in Greenland from 3.8 billion years ago. They kind of look like the messy zones where plates crash together. Others argue the real change happened around 3 billion years ago, when we see a shift in how the continents were growing. And then there's a really compelling case for a much later start, maybe only a billion years ago, which is when the classic telltale rocks of modern tectonics finally and clearly show up in the record. So why the huge disagreement? Well, it's because all the evidence is circumstantial. And to really understand why, we've got to get into the basic physics of what it actually takes to break a planet's crust and get things moving in the first place. Basically, rocky planets in our solar system seem to come in two flavors. The default setting is what we call a stagnant lid. You see this on Venus and Mars. They have a solid single-piece crust. The hot mantle is churning away underneath, but the surface itself doesn't really go anywhere. And then there's us, Earth. We're the weird one, with our broken shell and active plate tectonics constantly recycling our own surface. So the question is, what makes Earth so special? It all comes down to a kind of cosmic tug-of-war between two forces. On one side of the rope, you have convective stress. Just think of this as the raw power of the engine. Earth's mantle is incredibly hot, and it's always churning. That motion pushes and pulls on the crust from below, trying to tear it apart. The more heat, the more vigorous the churning, and the more powerful that pull. And on the other side of the rope is lithospheric strength. This is the resistance. It's just how tough the crust is, its ability to resist all that pushing and pulling. If the crust is strong, it can hold on, and you get a stagnant lid. But if it's weak enough to bend and break, you get plate tectonics. So here's the bottom line. For tectonics to start, the engine's power has to overwhelm the crust's strength. Simple enough, right? But, and this is where our whole investigation takes a really fascinating twist, because when you apply that simple logic to the early Earth, you run headfirst into a massive planet-sized paradox. I mean, just think about it for a second. We know for a fact the early Earth was way hotter than it is today. So hotter mantle means a more powerful engine, right? Stronger convective stress? And just like a hot piece of metal, a hotter crust should be softer and weaker. So a stronger engine and a weaker resistance, that should make plate tectonics easier, not harder. The early Earth should have been a tectonic playground. And yeah, when geophysicists run the numbers with simple models, that is exactly what they find. The physics says that the hotter a planet gets, the more likely it is to have plate tectonics. So, case closed, right? Earth must have had tectonics going from day one. Well, not so fast, because this simple, logical conclusion leads to a completely impossible scenario. If plate tectonics was running that fast on a super hot early Earth, the planet would have been losing heat at an incredible rate. And this leads to a problem that scientists call the thermal catastrophe. So here's the catastrophe. If you calculate how much heat the Earth would have lost going at that rate, and then you work backward to figure out how hot it must have started, you get temperatures that are just geologically absurd. The planet would have been so hot that it completely contradicts every bit of evidence we have from ancient rocks. The simple model just breaks reality. So this paradox sent scientists back to the drawing board. They had to come up with new ideas for why the early Earth's engine might have been less efficient than they first thought. One idea is called dehydration stiffening. The theory goes that the super hot mantle actually cooked up an incredibly thick and dry crust, and that dryness, paradoxically, made it much, much stronger. Another theory is mantle hydration. It suggests the early mantle was a lot drier because it hadn't had billions of years of water getting dragged down into it. A dry mantle is more viscous, think honey instead of water, which would have seriously reduced the power of the engine itself. Okay, so the theory is a total head-scratcher. But what about the hard evidence? Let's look at what the rock record, the actual library of Earth's history, has to tell us. And this table here, wow, this just lays the problem out perfectly. You see, some metamorphic rocks form pretty easily, but these high-pressure rocks, like blue schists, they're special. They are the key fingerprint of modern-style subduction. They only form when crust gets shoved down deep and fast, and then brought back up. And look, in the last 500 million years or so, they're common. But before that, in the vast expanse of the Precambrian, poof, they're almost completely gone. This is a huge clue. You have to ask, right? If plate tectonics was chugging along for billions of years just like it does today, we should find these high-pressure rocks all over the place in the ancient record. But we don't. Their absence is like this giant, silent piece of evidence screaming that whatever was happening on the early Earth, it wasn't the same kind of tectonics we have now. So where does all this leave us? We've got conflicting theories, a massive paradox, and a case of missing evidence. It all points to a really complex solution for what is truly one of science's great unsolved mysteries. It seems the solution isn't just buried deep in the mantle or hidden in the rocks. The growing consensus is that the answer is in the interaction between all of Earth's systems. Specifically, it's about the complex dance between the planet's internal engine and the water on its surface. Water acts like a lubricant for the whole system, and slowly feeding that water from the oceans into the deep Earth over billions of years may be what finally changed the rules of the game. And this quote from geophysicist Jun Koranaga just nails it. He's saying the story of plate tectonics isn't sealed off deep inside the planet. It's connected to everything: the size of our oceans, the height of our continents, even the air we breathe. It's all one gigantic, interconnected machine evolving together over time. And that is why this question matters so much. This isn't just a story about rocks. Plate tectonics is like Earth's global thermostat. It regulates our long-term climate, it recycles the nutrients life needs, it creates new habitats. So understanding when and how it started isn't just a geological curiosity. It's fundamental to understanding the entire history of Earth as a living, breathing world. And so, I'll leave you with this final thought. As we find more and more Earth-like planets out there orbiting other stars, the big question is always, could they harbor life? Well, understanding the unique story of how our own planet's engine sputtered to life might just be the key. It could be the secret ingredient in the recipe for a habitable world anywhere in the universe.